Hi, this is Dimitri from San Jose State University, and in this, I hope, brief video, I'm going to be talking about the inverse trig functions. Most of this video, these first two sections, are going to be talking about a very tricky, the particular trickiest aspect of defining inverse trig functions. So if you're a results-oriented person, you just want to see what the thing is, go ahead, fast forward the video. My feelings won't be hurt. And there's a slide that says the punchline, and you can just start there. All right, so I'll wait for you. Okay, so those of you who are left are of a hardier sort and who really want to understand what's going on, and so here goes. So let me first review inverse functions. Let me remind you that a one-to-one function, y equals f of x, is a function that never takes the same y value twice. In other words, y equals f of x is one-to-one exactly when any horizontal line passes through the graph of that function at most once. Remember, that's the horizontal line test. So another definition, if f of x is a one-to-one function, the inverse function f inverse of x is defined by saying that y is equal to f inverse of x exactly when, if and only if, f of y equals x. All right, so that's exactly enough that you need for the next few minutes. But if you want more detail, see the video on inverse functions. Okay, so here's the central problem with trying to define the inverse trig functions. We would like to find inverse functions for sine x and tan x, so because if there were such a thing, if they did exist, then their calculus properties would be very useful. But the problem is, here are the graphs of sine x and tan x. Well, we see right away, here's in red is the graph of sine x, and it fails the horizontal line test. Here's the horizontal line, y equals 1/3, and it crosses the graph of sine x actually infinitely many times. And the same thing is true for the tangent of x. Here in red is the graph of the tangent of x, and that crosses. And this green line here, just sort of randomly, y equals minus 5/7 also crosses the graph of tangent x infinitely many times. And so those functions fail the horizontal line test and are therefore not one-to-one. So again, the point here, the central problem with defining inverse trig functions is that neither sine x nor tan x is one-to-one. Oh no, man! They lied to us! It's a conspiracy, man! All right, so what is to be done about that? How can we possibly fix that? Well, as you might have seen from the titles at the beginning, we're going to cheat, but it's in the best possible way. So the point is, by restricting the domain of sine x and tan x, we can actually just force them to be one-to-one. That is, to be specific, and it's a little bit arbitrary the way we've done this, but this is standard, so everybody does it, so you might as well do it too. The functions sine x with domain minus pi over 2 is less than or equal to x less than or equal to pi over 2. And tan x with domain minus pi over 2 is less than x is less than pi over 2. And here we exclude plus or minus pi over 2 because the tangent of those angles is undefined. Anyway, those functions are both one-to-one, as you can see from the graphs. So here's the graph of sine between minus pi over 2 and plus pi over 2. As you can just see, this is one-to-one because any horizontal line will cross this graph at most once. And similarly, if I look at the tangent of x between minus pi over 2 and plus pi over 2, again, any horizontal line will cross this graph at most once. And so by restricting these functions, by reducing the values of x that we're allowed to stick into them, we just sort of by force make them one-to-one. I know it's sort of unsatisfying. I just sort of define away the answer, but that does seem to be the standard and actually really sort of morally correct thing to do. So as promised, here's the punchline. For minus 1 less than or equal to x less than or equal to 1, the inverse sine of x, or the arcsine of x, is defined by saying that y is equal to the inverse sine of x if and only if, exactly when, the sine of y is equal to x and y is between negative pi over 2 and positive pi over 2. And similarly, for any real number x, the inverse tangent of x, or the arctan of x, is defined by saying that y is equal to the inverse tangent of x if and only if, that is exactly when, the tangent of y is equal to x and minus pi over 2 is less than y is less than pi over 2. In other words, if you want to find the value of the inverse sine of x or the inverse tangent of x, what you do is you solve the sine of y equals x or this tangent of y equals x for y, respectively, but making sure that your solution y is between negative pi over 2 and positive pi over 2. And now for completeness, here are the graphs of the inverse sine and the inverse tangent functions. So, like I was saying, here's the graph of the arcsine of x, the inverse sine of x. And here's the graph, at least part of the graph of the arctangent of x, or the inverse tangent of x. I should say, just for the sake of completeness, that the arctangent of x is defined for any value of x. So if you keep on going, there'll be values up here that get closer and closer and closer to plus pi over 2. And if you keep on going as x goes to negative infinity, there'll be values here that get closer and closer and closer to minus pi over 2. But never quite reaching, because so you actually have a horizontal asymptote up here and a horizontal asymptote down here. But anyways, this is roughly what the graph of arctan looks like. All right, that's enough for now. Thank you very much for your patience and your attention. Go do something useful now. Goodbye, goodbye, goodbye.